Understood what is the unit of A0 and A1, right? A0 unit of A1 will be second to the power minus 1 and unit of A1 is second. Okay, that you can verify. You know the unit of M and K, you know. So please quickly verify whether you are getting the unit for this A0. Whether you are getting unit of A0 is second to the power minus 1 or not. Please quickly check it. Or it is written wrong here or not, just check it. Please check every word.
Yes, sir. Second inverse.
Second to the power. Okay. Anybody has problem in finding what is the unit of A0? No problem. Very good, students. Okay. So now, so if I consider that, so obviously since the M and K are the orthogonal to our eigenvectors, so I can very easily find out my modal damping ratio for the Rth mode like this for the mass proportional damping. Okay, because you see the for the Rth mode, so the diagonal term will be Cr, which is nothing but 2 zeta r omega r mr. Okay, mr is the I have not modified it. Okay, anyway, MR is kept here, MR cancel out, or if it's the, eigenvectors are mass normalized, then this will be automatically 1. Okay, if it is not mass normalized, then it will not be 1. Some values you will get. But anyway, both sides is got cancelled out. So I can find out zeta r is equals to n by 2 into 1 by omega r. Okay, so from this information, if I give you the modal damping ratio of any one of the mode, you can find out the constant A0. And once you got the constant A0, then you can substitute back it here to construct the modal damping, construct the damping matrix, which is mass proportional damping matrix. Similarly, for this also you can obtain, okay. And sorry, so and in this case, if I ask you to find out the damping ratio of any other mode, so you have to substitute the values of A0 that you already obtained, okay, and you have to substitute the corresponding frequency for which you want to find out the damping ratio. Then you can find out the zeta corresponding to that mode. Okay, so that is all are written here in a proper manner. Okay, that we have already discussed in the last one. So similar thing is applicable for the stiffness proportional damping. Okay, but and now if I plot these things, okay, that is the stiffness proportional and mass proportional damping. So you see this is the variation of the damping ratio, modal damping ratio with the natural frequency. Okay, but you see, you can read from this para that the variation of the modal damping ratio they represent, that means these and these are not consistent with the experimental data that indicate roughly the same damping ratios for several vibration modes of structure. Not exactly same, it is more or less same or little bit of difference, but not like that, continuously increasing or continuously decreasing like that. So there comes the Rayleigh damping or the mass and stiffness proportional damping, which is nothing but C is A0 M plus A1. Okay. So from the previous what we have obtained, so I can write zeta r is equals to A0 by 2 1 by omega r, and this one, right? This is for stiffness one and this is for mass one. So I just add it for the Rayleigh damping case, which is defined like this. So this is the popular Rayleigh damping matrix or mass and stiffness proportional damping matrix. Okay. So this is an improvement over the previous two. Okay. So in this case, Rth mode damping ratio is this. So obviously, since there are two constant A0 and A1, I need to specify at least for the two modes, right? Damping ratio for the two, modal damping ratio for the two modes. So let's say I am specifying zeta I and zeta j for the two modes, mode ith mode and the jth mode, whose natural frequencies are omega I and omega j. So I'll substitute that information here. I'll get two algebraic equations, simultaneous equation, solve it to get A0 and A1. Okay. Once I get A0 and A1, I'll substitute back here to construct my Rayleigh damping matrix. Got it? So I can construct C. Okay. This is the solution which is done here, and it can be seen that the Rayleigh damping matrix, the plot, if I plot here the frequency, natural frequency basically, versus the modal damping ratio, it is providing like this. And at least in the lower frequency range, like this range, it is providing more or less, close results which we are expecting from the experiment. Okay, the expected thing. Okay, as opposed to the only mass and stiffness proportional damping matrix. Okay, Now, usually what we do for the convenience, or since the experimental data are not available for many modes, what we do? We choose that the damping ratio for these two modes, that is omega I and omega j, are equal. So if the damping ratio, let's say, is zeta, okay, so for both the modes, if it is zeta, so then if it is zeta, that means if zeta I equals to zeta I equals to zeta j, so then it further simplifies, okay, the constant becomes this. So you should remember at least this expression, okay. So if the modal damping ratio for both the modes, right, omega I and omega j are equal, and that is equals to zeta, then I can find out a naught equals to 2 omega I omega j zeta by omega I plus omega j, and a1 equals to 2 zeta into omega I plus omega j, okay. You can read it. For practical application, modes I and j with specified damping ratio should be chosen to, you see, this is very important, right? Now the thing comes in your mind that which modes to choose, right? What is omega I, omega j? What is I and j basically, right? First mode, second mode, first mode, fourth mode. So obviously you understood our target, or our target modes is the initial modes, right? Initial few modes, which are very important for the response contribution, because they are majorly contributing to the modes, okay. Obviously for 1000 degrees of freedom we will not be worried about the 900 modes, 900th mode, okay, right. So that is the consideration, and in that case you have to choose the modal damping ratio of the two modes in such a manner that the other modes, other important modes, right, other importance mode modal damping ratio, right, that you can find out, right, any other mode you can find out. Once you obtain a0 and a1, you can find out the damping ratio of any other mode, right. So those damping ratio for important mode should be reasonable enough, okay, should not be abstract kind of, right. Let's say for example, so I have chosen for second mode and third mode damping ratio is 5%. Let's say these are my two important modes, and after I have calculated and I obtain a0 and a1, okay, and I find out that one of the important modes, let's say fifth mode zeta phi, is 50%. Let's say for example, so that is not reasonable, right. So you have to choose proper manner some other modes so that it's represent in a unique manner, okay. Okay, so let us say here one example is given, okay, and so in order to use this expression, right, this expression, that is for which the two mode damping ratio are same, okay. So which one in this case we are going to choose? We are going to choose first mode and the fourth mode. You see, omega 1 and omega 4, okay, because in that case these are more or less equal. Almost in this figure it is all equal, but you have to choose in such a manner so that it is becoming. We are not going to choose W2 and omega 2 and omega 5, because these are quite different, right? So in that case we will not be able to use that expression. Correct? Okay, so we are going to use W1 and W4, and you will see that W2 and W3 will be a little bit lower than that. It's okay, reasonably okay. And the higher W5 is slightly higher, and other higher modes which are not as it is important, because since the damping for those modes are high, obviously the response for those modes are quickly dies out. Okay. I hope it is written here. The remaining higher modes, 6, 7, damping ratio increase monotonically with frequency, and the corresponding modal responses will be essentially eliminated because of their high damping. Okay. So if I construct in that manner, that is C is my A0 M plus A1K, that is the Rayleigh damping, then I can find out the modal damping matrix. Okay, for the Rayleigh damping is obtained like this. Okay, that you can understand, right? A0, then U transpose M into U is an identity matrix. If it is a mass normalized, then U transpose K into U is a spectral matrix. There is nothing but diagonal of the eigenvalues or square of the Nusselt frequencies. Okay, just keep it in mind that this thing, Rayleigh damping, is assumed in most of the practical analysis. Okay. Okay, so there is an extended version of this Rayleigh damping. So as I already mentioned, or as you have seen already, so there are two constants, N0 and N1, and we need information of the two modes. Okay, so now if you want to include, so obviously your next thing come in your mind that why not to include more modes, 5 modes, 10 modes damping ratio, then our calculation will be much better, right? Okay, that you can, that is intuitively you feel that. Okay, so why not to include modal damping ratio of the 10 or 20 modes and just make a good formulation. Okay. Yeah, so there is an extended Rayleigh damping, or it's also called the Puffy damping. Okay, so that I am not going to discuss. Okay, just for the information, which I will tell you. Okay, so it is called the general form of classical damping matrix, or also known as the Puffy damping. Okay, or sometimes it's called the extended Rayleigh damping because it is extended from the Rayleigh version. Okay, so in this case, whatever number of mode you want to include, you can do it. Okay, right? You see, this can be actually lead. I mean, for special cases, this can be lead to the mass proportional, stiffness proportional, and damping proportional. Sorry, not damping proportional, mass proportional and stiffness proportional damping matrix, or the Rayleigh damping matrix, which is mass and stiffness proportional for different values of B. I mean, number of terms basically that you are considering in this summation. Okay, and the concept of this Puffy damping or the general form of classical damping matrix is by virtue of the that family of orthogonality relationship. Okay, family of orthogonality. Because you see, the idea that you are using is the orthogonality, right? In the Rayleigh matrix, Rayleigh damping also, right? Why we are choosing like that a naught m plus a1k? Because we know that m and k are orthogonal with respect to the your eigenvectors, right? Correct. Here also the similar concept is used here, and I think I have showed you, right? I have not discussed, but I just told you that there exists a family of orthogonality relationship. Okay, and I have given you the expression. Okay. Yeah, so recall, you see that equation, I don't know whether the equation number was same or not. So a proportional damping matrix can be made by any combination of these matrices. Okay, so this is just for information. You see, if you put b equal to 0, you get mass proportional damping. Just try to put in this equation b equal to 0, right? Okay, you see, so then this power will be 0 1, so a0 into m, right? A0 into m, b equals to 1. Okay, b equals to 1, so the m inverse it will be identity. Okay, then it will be a1 into k. Got it? So that is the stiffness proportion. B is equal to 0, b equal to 1. That is the first two term basically. 0 to 1 I am considering. Then you get this Rayleigh damping, and so on and so forth. You get the, you can include more number of modes. I mean, the modal damping ratio for many number of modes. But there is issues with the Puffy damping. Okay, whenever you are, but finally our aim is to, you have to find out this coefficient, right? So let's say for a Cauchy series, you will get a naught, a1, a3, a4 like that. Okay, so the solution of those coefficients are ill conditioned. So the matrix that you have to invert, right? That means I am talking about, go back. Okay, basically this matrix you have to invert, right, to get a naught, a1, right? This is the for Rayleigh damping. So similarly, for Cauchy damping, we will get, say there are 4 coefficients, so this matrix should be 4 by 4. Okay, so you are clearly understanding that in there will be terms like omega I and maybe omega I power 3, 1 by omega I power 4, like that. So you see omega I square and omega I cube and omega 1 by omega I power 3 or 4 has a large difference in their values. Okay, so that matrix may not be invertible in all the cases. Okay, and there are some other issues also there. Okay, so that is beyond the scope. So that's why it is, the Rayleigh damping matrix are most commonly used, and it is preferable by the engineers and the analyst. Okay, that's all. Okay, now the alternate question. Now very interesting, that you should have asked at the beginning. Okay, so now what we are doing actually, C naught, T C tilde, that is the modal damping matrix, is U transpose C into U, right? We know obviously this and this, that is the modal matrix, and we know this, right, from the what is called modal damping ratio, right? Modal damping ratio. So how to find out? Basically, you are trying to construct this matrix, right? So you can actually directly construct the damping matrix from this expression also. How to construct that? Obviously, C will be just taking the pre and post multiplication of the inverse of those matrices, right? So that is here U transpose inverse C tilde. Am I right or wrong? U transpose inverse C tilde. Correct, right? I want to construct this, right? That is the damping matrix I want to construct from the modal damping. This is the modal damping matrix, and this is our structural damping matrix. Okay, and this is the mode shape vector. That is the modal matrix U. Correct? I can find out, right? Now the question is that how to find out this and this. So how will you find out? How will you find? Everybody agree with me from this expression this is coming or not?
Yes, sir.
Yes. So how to find out? So basically, if I find out this and this, then this is the known, right? The diagonal of the 2r zeta whatever. Okay. Let's say I know this thing. So then how to construct the damping matrix? Okay. So I have to just find out the U transpose inverse and U inverse. So how to do that? How to calculate the inverse of U and the U transpose? So obviously you will tell the direct inversion, but direct inversion is not an efficient approach. Okay. And also if you do not consider the what full modes, okay, you have truncated it, okay, truncated mode, then it will not be a square one, right? You will not be a square one, right? So that will be n cross n hat, remember? Okay, so you cannot invert it. Okay, so the best idea is to use the orthogonality relationship again. So what is the orthogonality? U transpose M. Let's see if it is mass normalized identity matrix. Agree? Okay. Now, so I can say I can write it as how to write it? U transpose U inverse, right? So U inverse U, correct? Okay. So then if by comparing U inverse is equals to, right? So U transpose M, right? Yes. Okay. So I got it. And now take the transpose just of this. I mean inverse transpose and transpose inverse are same. So that will be equals to M. If I take the transpose of this equation, M transpose, that is M because the symmetric matrix, mass matrix. Very simple. Got it? So you see how quickly I got it. Okay. So this is just you have to take the transpose and multiply it by M. No inversion is required actually. And this is just M into. All agree with this expression? Any issue here?
No, sir.
Now you substitute back here. U inverse here, this here, and obtain C. So what I will get finally? Finally I'll get what I got. So this is transpose inverse, that is mu, right? Then C tilde, which is nothing but diagonal of 2 omega r zeta r. Okay, because I am considering the eigenvectors and mass normalized, and this is U transpose M, right? U transpose M. Okay, so that I can also write in some another form, that is I can write M. Now this is U, this is diagonal. Since this is diagonal matrix, that's why it is possible. So I can write summation of R equal to 1 to n number of whatever number of mode you want to consider, right? That is the beauty here. Okay, that is 2 zeta R omega R, because this one, the diagonal terms, and then this is nothing but UR transpose. Agree?
Yes, sir.
So this way also you can construct. Okay. So let's say, so that now we'll go through one problem and then it will be more clear to you. Okay. So let's say I've given you two modes. So you know the modal damping ratio of the two modes. That is for, let's say, first mode and the third mode. So omega 1 zeta 1 you know, and omega 3 zeta 3 you know. Put it here for this matrix. Also use the Rayleigh method, finding out n odd and n and check it whether you are getting the same result or not. Very interesting, right? Okay. Now quickly discuss about the non-classical. That is beyond the scope of your syllabus, but just for information, sake of information. Okay. So when if it is non-classical, obviously you understood U transpose C will be not be diagonal. Okay. Okay. Then how to handle it? So just in a brief manner, just I'll discuss about this. So when this type of damping matrix come into the picture, now when they are saying that the structure parts, the two or more parts of the structure has a significant different level of damping. The examples are given here like the structure and soil. So sometimes you do the soil structure interaction problem. Okay. So in that case, you see for the structure, it might have 3 to 5%, right? Concrete structure usually 5%, steel structure 2% or like that. Okay. But soil has a damping ratio around 15 to 20%. So there is a huge difference between the damping level. Okay. So in that case, if you want to do the combined analysis of the whole system, soil structure system, So your damping matrix that will be obtained will not be a classical type. Okay, that means it will not be diagonal. If you do the transformation, U transpose C into U. Okay, where U is obtained from the mass and stiffness matrix of the whole system. Okay. Similarly, another example is the concrete dam with water. So for water, the zeta is negligible relative to the dam, which is usually made of concrete. Okay. Then structure, it's additional energy dissipating devices. Sometimes we provide energy dissipating devices like damper, okay, to dissipate the vibration. Okay, or base isolated structure. Any idea of base isolated structure? I don't think so. Okay. Anyway, just it is to prevent from the earthquake damage. So he actually isolate the base of the structure by using some rubber pads or something like that. Okay, that is another issue. We are not going into that. So I am just I will provide these slides to you. You can read it from that, and they get just some initial idea, preliminary idea, and what is that. Okay. So in these cases, when there is a substantial difference in the two systems, and the resulting damping matrix is non-classical, so the better method is the substructure method. Okay, substructure method. That means you analyze individual parts separately and then combine them together. Okay, that is the called the substructure method in the simplest manner. Okay. So proportional damping matrices are suitable for modeling the behavior of most structural systems in which the damping mechanism is distributed rather uniformly throughout the structure, right? Which is not the case for these examples. Okay. For soil structure system or similar structure system, the distribution of damping forces will not be similar to the inertial and elastic forces. That is, the resulting damping matrix will be non-proportional. In these cases, damping matrix for the complete system is constructed by directly assembling the damping matrices for the two subsystems, for example, structure and soil. How to do that? Just for example. Okay. Let's say this is structure, this is my soil. Damping ratio 5%, 20 degrees. Okay. So I will do that for structure. I will find out first mass and stiffness matrix is related to structure, and mass and stiffness matrix for the foundation. They are individually proportional. Okay. But when we combine that, they are not going to be the classical. Okay. So C is for the structure, it is. Okay. So as per Rayleigh damping like this, for the foundation Rayleigh damping like this, then you can combine it and form the final non-classical damping matrix. Okay. So how to do the analysis for the non-classical damping system? Because finally you have to do the analysis. Okay. Right. To get the response. That is the aim. Okay. Remember, obviously this is not diagonal in this case. So if all the modes are to be considered, let's say, I mean, the system is very small and there are a few modes, and almost all the modes are quite important, and your accuracy is required for the work. Okay. So if you want to include all the modes in that work, so there is no other option but to just solve the equation of motion directly. Coupled equation of motion you have to solve. Okay. Using integration scheme. Okay. Right, because modal transformation will not make the equation uncoupled due to the presence of non-classical damping matrix. The mass and stiffness matrix will be uncoupled, right? But due to the non-classical damping, presence of the non-classical damping, it will not be uncoupled. Okay. And if you require the only few modes to be considered, then use the modal transformation, reduce the size of the system, and then solve it. However, again the equation will be coupled. The equation will not be uncoupled, right? I mean, what I am trying to say with this, the first point, you have to use the all n equations. I mean, all the n modes if you want to consider, then you have to directly solve the equation of motion, whatever you are getting, that is mx double dot plus cx dot plus kx equals to p, without any truncation. Okay, in simultaneous ordinary differential equation you have to solve. If you want to trunk, I mean, you see that only the first few modes are important. Why to solve in simultaneous equation? Do the modal transformation, but the modal transformation will not make your system uncoupled because of the presence of non-classically damped system. Okay, but your system size will reduce, right? That I already discussed. You transpose mu, right? If I use first n hat mode, n hat into n, this will be n plus n, this will be n plus n hat. So then what is the dimension? N hat cross n hat, right? Where n hat is less than n. Let's say you are using 100 mode instead of your total mode of 10,000 or 20,000. So system size will get reduced. Okay. So this will get diagonalized, but the C, if it is C there, it will not diagonalize, but still the number of equations simultaneously you are solving will be less. That is what I am trying to say in this point. Okay. Further, If you find out that your modal damping matrix after doing this transformation, obviously non-classical C matrix is non-classical, so it will not be diagonal. So you get full matrix you get. Okay. If you see that your non-diagonal terms are, negligibly small numerically as opposed to the diagonal terms, that means diagonal terms are predominant, then for approximation you can consider only as a, you can only choose the diagonal matrix and do what we already studied for uncoupled equation of motion. Okay. So that is what it is written here. If the non-diagonal terms for C tilde, that is the modal damping matrix, are much lower than the diagonal terms, okay, we can ignore them and solve the ensuing coupled equation of motion, so uncoupled equation of motion, because we are only concentrating on the diagonal terms, ignoring the non-diagonal term, if provided that they are much lower than the diagonal terms. Okay. So then it is the simple analysis, right? Uncoupled equation. Okay, so there is a lot of things to learn in this mode damping, and still people are doing research on how to estimate the damping or what could be the better damping model. Okay, so we'll just now solve one problem, but before that, just I'll take 2 minutes. So just to give one more information. Okay. So let me say this, like single degree of freedom equation. Let me write. Okay. Okay, x evaporation should I write? Okay, let's say phi vibration. Okay. So this is how many equations here? Come on, how many equations?
One.
Huh?
Like is there like single degree of freedom or multiple?
This is how many equations? Anybody please?
So n number of.
Why n number of? I am writing. Is it matrix form I have shown? Matrix vector shown I have?
So then it's single equation.
One equation.
Yes.
Second order equation, first order, third order fusion equation.
Second order.
So second order homogeneous.
Second order homogeneous, linear, ordinary differential equation. And it is a one, number of equations is one. Okay. We are considering a single degree of freedom system. Okay. Because I want to give one small information about that. Okay. This is equally applicable for multi-degree of freedom system also, but just for easy understanding. Okay. Let's say x dot, right? Okay. Let's say z1. Here obviously t you understood, right? So z1t is equals to, let's say, x1t, and z2t is equals to x1. Sorry, not x1. X, right? X dot t. Correct? I'm assuming z1t equal to xt and z2t equal to x dot t. Okay? So then, can I write z1 dot t, right? So z1 dot. So z1 dot t is equals to z2t. Correct? Is it right or wrong? Please correct me if I am wrong. Okay.
Yes, sir.
Just z1 dot t, right? It is okay?
Yes, sir.
That means 1 into, actually 1 into 1 will become a degree. Okay. Now here you substitute this equation, you write in terms of this z1 z2. So it will be what? So just write this equation in terms of z1 and z2 and tell me what is you are getting in terms of z2t and what is in the right hand side. Z2 dot t. So this will be mz2 dot t, right? The first one will be mz2 dot t, right? Plus c into Z2T plus K into Z1T equal to 0. Right or wrong? M into Z2 dot T. Then C into Z2T. I think I am correct. Correct?
Yes, sir.
Then what, tell me what is Z2 dot T? Z2 dot T will be minus M inverse K Z1T plus M inverse C, sorry, minus. So much mistakes I am doing. Minus Z2T. Anything else? Nothing, right? Correct? All are agree with this? Or not? Is it clear?
Yes, sir. Both are same.
Okay. Now I can write it in the matrix form. 0, 1, minus M inverse, minus M inverse, Z1. Agree? Agree, right? Or in matrix form. Defining that ZT as this. Z dot, where Z is equals to, ZT is equals to Z1, Z2. Agree with this expression? Defining Z like this. Okay? This dot. So here my ZT is nothing but Z1T, Z2T, that means my displacement and velocity. Okay. So this equation. So what is this equation? This is first order or second order? This first order or second order?
First order.
First order. So this is first order equation. How many equations?
Two equations.
Two equations. One equation, second order, one equation, first order, two equations. In general, second order n equation, first order two n equation. Okay. This equation is called the state space equation. Okay. Just remember the terminology, nothing more than that. It is actually should not be discussed at the BTech level, but just for the sake of information I have given you, you might encounter in your future when you read some literature or some papers, journal papers like that, you might encounter that they are writing the second order differential equation in the first order equation because it has some applicability or advantage of using the first order equation, like for control theory, vibration control. Okay, vibration control structure, or in electrical engineering purpose, modern control theory, people write equation in the first order equation, usually in that form. Okay, this is not the complete form. If there are force term there or some other term there, then there will be some plus is there. But we convert this second order equation to first order equation, and this is called the state space equation. State space, why? Because this Z we call the state of the system. Because why it is state? Because it is the displacement velocity. It can represent the system state at any time. Okay, and E is called the system matrix. Okay, because it involves the system parameter, that is MK and C. Okay, and actually these type of formulations are useful if your damping matrix is also non-classical. So then we and we go for this type of formulation. Okay, just for the sake of information. Okay, done. So now please solve the problem if you have understood everything about the Rayleigh damping or classical damping. Okay, if you have asked, if you have doubt, you can ask me. Problem quickly. Very simple problem. And similar type of problem, at least one problem will be given in the any one of the upcoming exam. Okay, similar type of, and there is very straightforward. If you solve it, you will find out. So I will ask everybody to solve this problem. Okay, There is nothing complication here. Okay. If you have still doubt regarding the Rayleigh damping, not the non-classical damping, all those things, if you are interested, that you can ask me later. But those are not part of your immediate syllabus content. Non-classical damping matrix or whatever just I discuss about the converting to the second order differential equation to first order equation, writing it in the state space. So this is just for your information.
Sir,
Yes.
so value of omega and so for finding the matrix.
What you are asking?
The values of omega.
Omega you have obtained already. What you are trying to say? Omega you obtained or omega you are calculating what?
So like for finding coefficients, we'll need that omega, na? Omega 1, omega 2.
So how to find out omega?
Okay.
It's a three-degree of freedom system, right? It's a lump mass shear building. This type of building is called the shear building. Rigid floor. The three masses are given there. Story stiffness are given there. K story means basically you can write. I mean you can write this one. You can write like this. The three masses. This. This is also spring. This is K1, K2, K3. All are same. 1000. Remember carefully. This is kilonewton per centimeter. Okay. And these are the masses. Whatever M1, M2, M3 is given here. M1, M2. All are given. Any question? Any question? No question. Please solve. Okay, so just one question. Do we need to find our mode shape or not for this problem, to solve this problem? Obviously, we need frequency, as someone just told, the server is the frequency. Do we need to calculate mode shape or not? Is it required or not for this present problem?
So only like the omega are required.
I am asking the question, the mode shapes are required or not? My question is clear or not, first of all?
Sir, no,
This-
sir, mode shape is not required.
Yes, that's all. That is. So please everybody do the problem. So with this actually finish the damping formulation for damping matrix. Basically we discuss about the formulation for classical damping matrix, right? That is the proportional mass and the stiffness proportional, that is Rayleigh damping. So that actually you have to remember what is Rayleigh damping. That is good enough for your level. Okay. So next class onward we will start how to calculate the natural frequency and the mode shapes using some technique. Those are commonly used previously and also important to understand also those things. So few methods we'll discuss, and like the matrix iteration method, Jacobi method. What is the method name? And one more method is there, and then obviously Rayleigh, again the Rayleigh method. Okay. That is very interesting. We'll discuss. Okay. Determination of the natural frequencies and mode shapes. Holger method. Yes, I remember Holger. Holger method, matrix iteration method, Jacobi method, and Rayleigh method. So these few methods we'll discuss. And once we finish that, we'll move to our last topic, that is the continuous system.
So what is the final answer for this?
What is the final answer?
Yes, sir.
N or D1, can you see it?
Yes, sir. And then zeta will be 6%.
No, N or D1, you got correctly?
Yes, sir. I got 0.8%.
The result you got right, whatever it is written here.
Yes, sir. I got it. I got 0.8%.
Point?
847.
No, you take please to the more decimal places, okay, for accuracy.
Okay, sir. Zeta will be 6%. Approximately.
This is C matrix you got.
C matrix I didn't calculate, sir.
So calculate and check it. Be careful about the unit written here. So all are able to get A0 and A1, because once you got A0 A1, it's just very simple, right? Then you can find out C equal to A0 M plus A1. M and K2 you have already obtained, because in order to find out natural frequencies you need M and K. Okay. So just check whether you are getting A0 and A1 correctly or not. Once you got A0 and A1, you can find to construct the damping matrix C like this. Okay. And then any other mode, I mean in this case any other means the third mode is remaining. First mode and the second mode damping ratio is provided to you, 5% damping ratio. Modal damping ratio is 5%. Okay. So third mode you can find out, right? That zeta 3 is equal to, right? Because you know already A0 A1, so you have to just provide the information of the third mode natural frequency, and A0 A1 already calculated, you can find out the third mode damping ratio. Okay. So just basically you have to calculate A0 A1, that is the primary goal. So all are able to find out A0 and A1 correctly, or any issue in understanding the problem. If you do numerical calculation problem, that is different thing that you can rectify by yourself. But difficulty understanding the problem or not able to visualize what to do and how to proceed. If you have still any question, you can ask me. I'll be here for 2-3 minutes more. Those who have already done, okay, or those who do not have any question, they can leave. There is no
Sure.
problem.
What is the final answer for damping ratio?
C you got correctly?
I got A and B correct. I mean A and A not correct.
Then so obviously then you will got C, right? A not M, just you have to multiply it. A not M and A1 can add it, right? Correct or not?
Yes, sir.
Yes. Zeta 3. That is zeta 3 is 6% around, right? 6%. Okay, so I'm again repeating, those who have any doubt in understanding the problem, they can still ask me. I'll be here for a few more minutes. Those who have already done the problem or do not have any doubt, they can leave. No problem as such. Okay. Tomorrow we'll start with the determination of the natural frequency and motion using few methods like Holgen method, Dunkerley's method, Rayleigh's method, matrix iteration method, and Jacobi's method. Then after that we'll move to our last topic, that is the continuous system, and only we'll discuss about the beam vibration, and that is also Euler boundary beam. Okay, not the demotion curve without shear deformation. Right? Everybody understood, I think. I will just keep this slide here. This is the state space formulation just for your information, but that is